Hello, everyone. Welcome to the class Mathematical Analysis. I'm Nicholas. You can also call me Ching, Rebel, anything. Because I have so many names, I cannot remember them well. And I'm already graduated from University of Washington Mathematics. I will give a brief introduction of myself. I study probability, optimization, linear, nonlinear, discrete, and non-discrete, and also real analysis, complex analysis. But I like real analysis more. I think it's more, firstly, it's easier to understand and I have more applications in mathematics field. And this course is called mathematical analysis. So it mainly contains two parts. As you can see, real analysis and complex analysis. And we can see from below, we'll first talk about logics, which we will this will go through it today, and we'll also study set. Set you probably heard of it from high school already. Function, yeah, function like y equal to x squared, and number theory. While number theory might be a little bit like scared to most of you, but it's mainly about modulus and the prime number. So I think that'll be relatively easier to understand. Sequence, series, well, that's like 1, 2, 3, 4, 5, 6, or 1, 4, 9, 16, 25. If you can recognize the pattern, that's sequence, and series is a summation of the sequence, which we will talk about later. And the next topic is calculus, differentiation, integration. Well, you may heard of it if you studied calculus before. Matrix space. Matrix space is like a multi-dimensional version of the real line analysis. It's like instead of open interval, closed interval, we talk about open ball, closed ball to n-dimensional space. Norm space, that's like another type of matrix space, which the distance can be measured in norm. And this will introduce to the major theory, which is, well, what about a point length? If we know it or we don't know it, that's the major theory. And we can figure out, if we can figure out some part of real line is measurable, we can do the best integration, which is also called the best measurable set, or the best measurable function. And this is all the real analysis part. But I don't think we'll go that deep this summer. We'll only go to maybe, no, not matrix space, the first six part, go to calculus for this summer, because summertime is limited and this is a lot of stuff. This is like math 300, 327, 424, 425, 426, 427, 428, which is 7 class in University of Washington, which will last about 3 years. So in the summer, it's impossible to teach that much. And for complex part, we'll talk about Cauchy, the big Cauchy theory, the general one or the limited one, and the Cauchy integration. It's like doing integration or differentiation. Well, you can call it differentiation uh based on the real analysis counterpart, but it's also called like it can be also called the uh what's called analytic function. The Lorentz expansion residue theory, followed by, if we can calculate the negative one, the negative one coefficient of the Lorentz expansion series. Maybe I'll talk Fourier transforms first. Conformal mapping, that's too hard. That is still what I'm still figuring about. So maybe I'll talk about in the end, maybe summer 2025, summer 2026. Who knows? Because 2026 there will be a like the World Cup for soccer in Seattle. So maybe I will not teach in that summer, but maybe I will, because I like to do that. I think it's very valuable. So this will be a very introductory course to mathematics, but as you can see, it will go really fast, with a fast pace. So if you don't, if you like, just miss several lectures, you will probably don't know what's going on, for the later part. So it will be about in a quick pace. But if you don't know anything about math, only know, well, I read English, I listen to English, I can speak, I can write, and that's a starting point for you. So we'll go to some basic definitions in mathematics. So the first definition is statement. Statement is English sentence. So if there's an English sentence like, well, Coca-Cola mm, is a type of beverage, that is definitely a statement because it states like Coca-Cola is a beverage. It's true. It's true. So it can be true, can be false, can be both true and false, can be neither true nor false. For example, something is it's very clear. It's like Coca-Cola is a beverage. That's right. But if you say, well, I think Sprite is better than Coca-Cola. So this might be neither true or false because it's undeterminate based on different individuals. So in this case, it's still a statement, but it will not be a proposition. Proposition is a sentence that can only be true or false. So that's the difference. Okay, the next one is axiom. Axiom is also statement. So everything is statement from now on. We're not talk about sentence or words, but statement. Axiom is statement that is always true. That is agreed to be true by common sense. For example, you can think about, well, there's a famous axiom we'll talk about later called positivity axiom in real line. So that means there's only three type of real numbers, which is positive, zero, and whose negative is also positive. So that's the three different kinds of um real numbers. Okay, so axiom is always agreed to be true. It's very basic, and it's you can say, well, uh sometimes like theorem is based on the deduction of the axiom. So that is the next level we'll talk about. And also proof. Proof, everybody knows like mathematics is full of proofs. So if we want to prove something to be true, we always begin with the axiom that we know is true already. And then we'll talk about in the later part, we'll talk about three main proof strategy, direct, indirect. That's the next part, but proof is just a process of proving some, like making some new statement to be new axiom probably, or we can say it's a theorem. So logic, logic. I think this definition is what I learned mathematics at the beginning, but I don't think it's important. It's just like just like some random words to say. So if you read it, just read it. So theorem, okay. Theorem, what's that? Theorem is a statement that is already proved to be true. So we know that from number three that proof is make new true statement. So if it's already made, it's already proved, then it's become a theorem. A proposition here. Usually in mathematics, proposition can mean two different things. You can think about proposition as a statement either true or false, or which is unlike basic statement because it cannot be neither true nor false or both true and false. For example, Sprite is better than Coke in taste. It's not a proposition because well, you cannot say whether it's true or false. But if you say X let's say 1 = 2 is a proposition, it's false absolutely, and it's not an axiom. If it's true absolutely, then it becomes maybe it's an axiom, maybe it's just a basic result, like 1 ≠ 2 is that an axiom? It can be an axiom that choose by yourself, but it's not an axiom agreed by most mathematicians. So that's the difference. Okay. And some based on the truth values, okay, we are not talking about truth values so far, but we'll talk about what's true and false from now on. And choose companion. What is choose companion? Well, it's like it's a pair of sentence because companion in English basically means, well, it's there's one part, there's a second part, and they are with each other. they're with each other. So if you say keyboard is a musical instrument, or maybe keyboard have different meaning. Okay, so piano is a musical instrument. What is its true companion? That is, piano is not a musical instrument. So one of them is true, one of them is false, and that's like a counterpart of both. And the next part is truth value. So now we talk about truth value. So the proposition, which is can only be true or false, and we can label them as true, label them as false. That's like, I think that's a basic idea. Or if you cannot understand what's true or false, just think about like in common sense, what you think is true or false. Like mouse is red. This is a very intriguing part because mouse can be red. Mouse can be red in some cultural backgrounds, but in Seattle, people usually think about mouse are pretty small, but reds are huge. So so that's not a good example, but you can also label it as true or false. All right. So the last part is very important. The last part is about choose functional. So this is like a function, if you know it already. Function like have input, have output. So choose functional is a other adjacent that describes something can be viewed as a function. For example, n can be viewed as function because a and b. If a and b, if a, b, a true, b true, then a and b is always true. But a because b is not always, is not the case because a, b can be true, but the because, well, the because relationship is not depend on a and b. So the same input can result in different output. So that is not truth functional. So let's see example. A is equal to 1. A is defined as 1 plus 1 equal to 2. B defined as 1 not equal to 100. C is 2 plus 2 equal to 4. So from this view, all we can see is that um A and B is true. Yeah, because both of them are true. And A because B is false. A B because B, well, because doesn't stand here. Why 1 not equal to not equal to 100 can determine 1 plus 1 is 2. So that's not a wise idea. C because A, this can be true because 2 plus 2 equal to 4 is based on the logic of 1 plus 1 equal to 2. So we can see A, B, C both true, but A and B, A because B is false. C because A is true. So so the because is not truth functional. And can we determine that it's truth functional? There's infinite examples. So maybe I'll define a different way and see later. There's some other type of like theorem. Theorem is proof truth, right? So, but there are other nouns to describe it. Lemma is usually it's not very important theorem, but it's a theorem used to proving other result, other statement later. So that's what we call the lemma. Yeah, that's the lemma. And the corollary. So what's corollary? Okay, so corollary is direct result from something, from a very big theorem, which is important. Directly follow, not usually write 1 or 2 lines of proof and it can be proved. So that's a corollary. Conjecture. Conjecture is something we think, well, it is true, but we cannot prove it. We just accept it. For example, 1 is not equal to 0. This is a conjecture, very famous conjecture, because we always think about 1 different from 0, but from the basic axioms in mathematics, we can, I believe is from today or maybe from last week, it's not proof that 1 is not equal to 0. So this is a fun fact. You can also view it as a hypothesis, but this is different than hypothesis. Hypothesis have a low probability to be true, but conjecture is we already view it as true, but it's unable to prove it yet. So that's like 12 definitions of like in mathematical language, people always talk about in college in academic field. So if you don't know it before, it's very fine. Because I don't know it until my second year in college. In my first year, I always learn calculus, like all right, it's a function, there's a derivative. What's the so I never touch about these things until my second year of college. So if you know it now, you have a quick beginning. And so the main topic for today is logic. We'll talk about how to represent English sentence, English word in mathematical language, and how to think about mathematical logics, which is slightly different from uh, the common logic, the common sense logic in your life. So one important thing to begin with is called a statement form. So what is statement form? Statement form is, well, statement form is you can always abstract some English words or English sentence out. For example, you can see here, 2 is not an imaginary number. So this is what we say about. So we say about they like, hey, the square root 2 is not a imaginary number. This is very common. But if we write that in mathematical language, they'll be very long, very tedious. So we always use some notation, for example, A or PQRS. That's common denotation to denote the long sentence. That is just like use X to denote unknown numbers in elementary math in your study before. So let's just use it. And I'll talk about the five basic logic trend in mathematics. The five basic mathematics. So what are they? The first is negation. Negation is meaning not something. So it has two denotion. One is the it's a wave line or just like a right angle one. I prefer to use this one. Some people use this one, but both of them means not something. So if P is true, then negation of P means false. That's the rule. So let's see an example. If P, we denote P as this sentence, 2 plus 3 is 5. This is true. And if we put a negation on it, it is not the case. It is not the case that 2 plus 3 equal to 5. And this is the same as we say, well, 2 plus 3 is not 5. Is that in common sense to be true or false? I think it's false. I think it's not correct. 2 plus 3 is just 5. All right, so that's the negation. Negation, very common, very commonly used. And I think the most commonly used is negation uh to controvert something. And the second one is what we left before we talked about is and the truth functional. So here we define it as the conjunction. Conjunction is denoted as P and Q. P and Q. So this notation is how to say it? It's well, you can think about it's just and. It means and. And it's very similar to this one, which is in set theory, the intersection of something. So this is the notation P and Q. So what's the logical rules here? Logical rules is if if P and Q are both true, then it's true. Otherwise, it's false. So if P is true, Q is false, and it's false because it's not both true. So let's get example. You may not see this before. This one is this one is empty set. And it's the subset of every set. So set we'll talk in the second lecture. But I assume you already know a little bit about set. Okay. So this is the subset subset of every set, and Q is two belongs to the empty set. P is true, yeah, but Q is false because 2 is not belongs to it. If 2 belongs to it, what happened? If 2 belongs to it, then this set is not a subset of empty of something of some set. Well, we can see of some set in the sense of like nothing in it. So that's why it's false. Okay, so that's the conjunction. And the third one is very intuitive. It's or. It's or. P or Q denoted as this thing. Wait, it's like a B, and this is like a lambda, the capital lambda. So disjunction logic rules just the opposite. If P and Q are both false, then P or Q is false. Otherwise, it's true. So that's its logic rule. So let's say typically or has two meanings. Let's talk about this. So if you think about I will think about the scenario. I will give you a free laptop if you pay me pay is not free. So if you give me the correct answer of this question, or you give me a diamond ring. So there can be like or in between. So this or is in this scenario, or is inclusive because if you both give me the diamond ring, or you uh um or you like solve the question correctly, then you can get the laptop for free. But in another scenario, like you can just select if you go to a restaurant and ask coffee or tea. So that might be not both because you only pay them like, for example, 1 cup of something, the price of 1 cup of something. So in this case, or is exclusive, which means you can only pick one. But in mathematical language, or is always inclusive, which means the both case is true. So that's why we can say like P or Q is true if it's like both of them is true. If it's exclusive, think about it. What will happen? What will happen? If you think about it, you will find out when both is true, then it's false. The result is false. So that's the big difference between inclusive or and exclusive or. Okay. The first one is conditional proposition. It's like if something, then something. If P, then Q, or P implies Q. On Q, also sometimes say P is necessarily for Q. Sometimes I remember. I just guess it. So what's the logical rules is the truth of P and falsity of Q doesn't coexist. So think about it. If P is false, and Q, if P is false, Q is true, then what it means? It doesn't matter because we assume if P is true, so we are only consider the truth of P and true or false of Q. But if P is true or Q is true, then if then works. But if P is true but Q is false, then absolutely it doesn't work. So it doesn't exclude one scenario, that is P is true and Q is not true. Okay, and some other expressions can be written as this one. This is funny. The conditional proposition, which is one arrow, but you can also use negation and conjunction to denote it. This two, you can also write it, but I don't think it's very common in mathematical language in my life. So you can just view about it. But I don't know if it's you will see it later. I will always use the this type of arrow, the type of arrow here. This one. This one is what I denote the issue. And y is equal to this. I can left as a exercise for you to think about later. Why this arrow is equal to this one. It's very easy to think about. Just use the truth value I talked about before. Okay, so so the visual expression is if P then Q. Q is a outside it's an outside set of P. So why is that? Because if P then Q, the truth of P and falsity of Q don't exist. So Q must be larger than P. Q cannot be smaller than P. If Q is here, then the falsity is here. Falsity and the falsity of Q and true of P is coexist. But so this is why Q must be larger than P. And why this part actually work is to think about it this way. This is true and P is false, but in if and then sentence, the falsity of P doesn't matter. So which means Q can be much larger than P, but it cannot be a subset of P. It cannot be a real subset or smaller, strictly smaller than P. So okay, so that's conditional proposition. And the last one is called biconditional proposition. Let's talk about this one. You can see very a slight difference here is a one-sided arrow and here's two-sided arrow. So it's easy to think about it as like both way. It goes both way. It's if P then Q and if Q then P. So so this one is can always viewed as and going backwards. Yeah, I think it's correct. It's you can think about it in this way. Okay. And this and the biconditional proposition we usually denote it as if and only. If and only. Or more commonly we say if the long F, the double F to denote the if and only relationship. So logical rules is P and Q must be at the same value. So P true, Q must be true. P false, Q must be false. And that's the only how to say that's the only thing we need to consider about. And all right, let's see. If you want to show like the biconditional proposition is true, you can just show both P goes to Q and Q goes to P is true, which is just illustrated as like forward and backward, and both of them is okay. So let's see example. I is imaginary. If and only 10 minus 10 is 0. This can be like very not like not common sense. This is not common sense because when you talk about imaginary, you don't well, who can think about if a minus equation here, 10 minus 10 is equal to 0? But they are both true. I is imaginary. Yeah, I is imaginary. And 10 minus 10, absolutely, it is 0. So true, connected by if and only if it's true. So this is how we view a sentence in logics. So in common sense, you will see, wow, what does it mean? What the fuck is this? But in logics, if you follow the rules of if and only if, then it works. And the next topic we'll talk about statement form. But yeah, I want to ask if you have questions so far, you can just ask me right now. Okay, so So let's go to the statement form. So statement form we already talked about in the beginning. We already talked about here. We can use capital letters to denote a sentence. And here is a different situation. Letters denote sentence, expressions, logical connectives, and we already read before. This is uh or this is and, negation, if then, if and only if. These are called the logical connectives. And parenthesis. Parenthesis is this one. We never use the square bracket or the this type of bracket in logical connective in the statement form. So these three are used to denote the statement form. All right, and let's talk about how it usually looks like. So we can see some examples here. In this example, in the first example, Q or not P. Is this correct? It is makes sense because not P. They have enough bracket to denote it. You can see it here. There's one layer. This is one layer, two layer, three layer, and four layer of bracket of parentheses to connect it. So this is correct. A and B goes if A and B, then E. A, B, E are English sentences. And in this case, it is a statement form because it makes sense. But here we can see S and not R is not. This is not statement form because it doesn't make sense. What does the parenthesis here mean? It doesn't have some backward. And S and what? We don't know. So this might be false. This might be a randomly typing words. This is also not what. This is left blank. So this is not statement form. Only statement form that is fully determined, fully defined, and fully understandable. We call them statement form. Okay, and we talked about truth value before, and how the rules for the PQ for such logical connectives works, how it works for PQRS. So in this case, we'll talk about truth table. Well, okay. So what is truth table? First thing of truth table we need to consider about is let's say it's always a table, two-way table. Here we always place P and Q in the left side, and what we want to determine at the at the right side. But here, all of them we want to determine, so they are all on the right side, place here. So this is the truth table. Truth table is very effective. You can see it very clearly if you want to see how if you choose P and Q to be both true, what is if then relationship is true. You can check it here. So let's see about how it works. If it's both true, then not P. Not P is false. P and Q is true. P or Q true. P this is true because P is true, Q is true, PQ both true, so it's also true. So you can check it in this way. And for example, we see P is false and Q is true. First thing we can notice is the negation of P, not P is true, becomes true because it's false. The negation of false is true. Okay. And for the AND problem, one of them is not true, so it's false. One of them is true, so it's true for the OR. And if then, because the beginning the if statement is false, so it doesn't matter it's true, but it doesn't equal, so it's false. So this one is also correct. So we can always check in that way to for every truth table to determine if it's a truth functional. So let's see here why we can say and is truth functional, because if PQ are true, then it's always true. If they are false, then it's always false. And each combination, each possible combination, we can see here 1, 2, 3, 4. There are 4 possible combination of 4 possible cases, and it turns out to be all of them are constant with constant result. So in this case, the only way to prove something is truth functional is through a truth table in this way. Okay, and perhaps we are going to see our first theorem, the first ever theorem in this course. Is the theorem here listed here. If a statement form consists n sentential variables, then there will be 2 to the power of n rows in all. So let's think about it. Why is true? So here we can say how many sentential variables here? There are 2, p and q. 2 to the power 2 is 4. Yeah, it has 4 rows here because each p have 2 situations, T and F. Q have 2 situations, T and F. And we use 2P is equal to T to each connective to the Q is equal to T and F. So here is like T to the T, T to the F, F to the T, F to the F. And they're going from some single start. So it means it looks like a decision tree model in logics. But we can also consider it in a different way. So let's think about it in this way. There's n digits of T and F variables. For example, you can say about this is A, this is B, this is C, D, E, F, G. And it goes to the end, there's some like chi, there's a chi. All right. And there's n digit in between. Each of them can have different T or F, but there's only T and F possible. So A have how many possible cases for A? 2, T, F, B, T, F. So it's like a so we can see here, it's like we can apply the multiplication rule in like selection determinant. So it becomes 2 times 2 times 2 times 2 times 2, 2. There's n digits. So they're in terms of 2 multiplied together, which is 2 to the power of n. So this question is solved in this way. So let's work with one example here. So what is this example? Determine the truth value of the following statement form. Let's say A is a new variable, is equal to P and Q negation and P and not Q or not P. Seems very complex. Seems like a complex example. How we solve it? Is usually use the truth table. So we said because we know there's only 2 different variables P and Q, so there will only be 4 rows. It's solvable. There's limits, very limited. You can even write in hand in this way to think about it. So first write P and Q and figure out what's P and Q and what's not Q, what's not P, and what's not P and Q. this is every step from going from the left side to right side. Q is from here and P is from here. And this one is like not Q and not P, goes to here. And not Q, not P, and Q and P is from starting to go here. And what's A? A is determined by this one and this one. So we know what's A here. And we always check the rightmost column, this column, to see its result. So first get rid of this one. So back to the problem. What we need to find is the truth value of the following form. So it can be false most of the time in 3 cases, and true only if and the statement variable A is true, if and only if P and Q are T and F. So that's the result. However, we can see why we need to consider this as A. A is very complex. You can work it too many. However, you can observe an interesting fact here. A is equal to P and not Q. P and not Q is also have the rightmost column as this one. So, well, they're equivalence. So we call this the logical equivalence. We define it here. What is logical equivalence is if S1 and S2, suppose they're two different logical representative, and S1 is equal to S2, S1, S2, if and only if is always true. So which means their true times and false time is always occur simultaneously. Okay, so based what we already know about logical equivalence, we talk about tautology. Tautology is if the substitution of propositions for a sentential variable always have a true proposition. Or on the truth table here, the rightmost side is a connective T. It's like T, always T on the rightmost side. Then it's a tautology, which means like it's impossible to be false. It's 100% to be 100% to be true. And we can see one example here. P, if and only if not P. Is this a tautology? Is this always true? Let's see if P is true. Then true, this is true too. Yeah, works. And it's false, this is false. And this side, not false is false. And they have the same truth value, so it's also true. So this is tautology. And definitely as an exercise for you to determine these three. These three are all tautologies too. So you can see if you can figure it out or not. I think it's pretty simple to use the truth table and use the truth value we said before to do this too. And we brings one notation. If we say S1 is logically equivalent to S2, the logical equivalent symbol is this one. It's usually we write equal is this one, but we add one more to say it's logically equivalent. So that's the denotation here. And there's some basic logical equivalence you can just view it associative laws, commutative laws, idempotency laws, absorption laws, distributive laws, laws of double negation. Those are, I think, is very familiar with what you learned in high school. But the Morgan's law, this is new. This is new to most of you. So I will talk about it. De Morgan's law says not P or Q is equal to not P and not Q. And if the not outside, the inside is or, then it is logically equivalent to not P or not Q. So and becomes or becomes and the not is separated into two different settings. This is De Morgan's law. And also, you can use your knowledge to prove if it's actually logically equivalent, but it should be simple as above. The next important principle I'll talk about is called the replacement principle. If there's already exist one logical equivalence, say S1 equal to S2, logically equivalent to S2, and S1, one of its component, and S1 is one of the components in a more complex statement, S3. So let's write it in this way. S1 and S10, for example. This is S3. And now we'll replace it to be S2 and S10. And the new resulting one, we call it S4. If S1 is logically equal to S4, then S2, then S4 is logically equivalent to S3. This is the replacement principle. We said, like, if you can always find the logical equivalence part, how to say it, if you can always find S1 logically equivalent to something, S2, S10, S100, anything, and they're like you can replace it in a more complex one, and there's always true. So here we'll give one example here. So based on the absorption laws, A is logically equivalent to A and A or B. So we can do the following replacement here. So A and A or B. If A and A or B, then C is logically equivalent to not A go to C. And the logical equivalence posed by the principle above, because we replace this one with A by this statement here. Okay, and let's go to the next part. This is the last part of today. It's called some proof strategies. Here. But here is like a principle law of logical statement. Oh, it's always say, and this is easy to understand, it's always use simple statement form to denote a more complex statement form. For example, as you studied in high school, cosine 0 is equal to what? Is equal to 1. E to the power of e to the power of 0. This is 1, 2. So this is 2. But why not write it as 2? 2 is simpler than the later one. So this is the principle of logical statement. Use the easier and simpler one. Okay. Let's talk about the last part, the proof strategy. In mathematical language, if you want to prove something, if you want to show your result is correct, uh, proof can be very difficult. I must say that. Looking back to my mathematical practices in undergraduate, proof is the most thing that made me want to made me nervous because I always don't I'm always not sure if I can figure out this or not. Proof is hard. But there's some basic trend, basic movement that lead you to think in some way. The first is direct proof. Direct proof is if you want to show statement Q is true, you can always first show P is true, and if P, then Q is true. This is because like if P is true, Q, and this one is true, then Q must be true because if Q becomes F, what happened? P it goes to Q is not true. So proving P true and if P then Q is true is equivalent. It's logically equivalent to proving Q is true. So this is what the reasoning here. And the direct proof is also called the law of detachment. Direct proof is the most intuitive one, and the two strategies later is more interesting. First one is called the proof by contrapositive. If you want to show that P goes to Q is true, this is a very common statement in most mathematical languages. You want to prove if something, then something is true. Then one strategy called the proof by contrapositive is to show not Q is true, and then seek for not P is also true uh based on the information that not Q is true. We'll see one example later. And the reason here is that when Q is false, P has to be false in the conditional proposition. So if Q is false here, if Q is false, and P and you want to prove this true, and P have to be false. Or what happens if P is T, then T goes to F. This part is false. So that's the reasoning here. All right. And the last part, oh my God, last part is the most abstractive one. Proof by contradiction. There's a lot of contradiction in life. Life is full of contradictions. But to prove Q is true, we just want to show the negation of Q is leads to some contradiction, leads to something that is not true, not false. Well, uh, this one can be pretty hard to determine and can be I think this is very abstract. But I have one example later to see this one. So what we just see the examples here. If n is an integer, we can try to prove something. If n is an integer, then n to the power 2 is even, which means n is even. So this is a if then statement, right? So how do you prove it? If we use the proof by contrapositive strategy as we illustrated here, so not Q implies not P. So we'll try to prove n is not even. N is not even goes from here, and then n squared is not even. So this is we transverse this statement into this statement for the control positive strategy. All right. So now the question becomes this one. This is our new question. So how you solve it? Because integer can only be odd and even. If you don't believe it, just accept it. Because I think this is what you already learned in high school, middle school. odd number and even number. So n is not even, which means n is odd. N is an odd number. Then what happens? Then n is in the form of 2k plus 1. Why that is correct? Because 2k is always even. And even number plus 1 is always odd. Or 2k minus 1 is odd. So that's for any k is integer. So that's what we want to express the odd number as illustrated above. So when we think about it this way, then n squared, n is odd, is here, and n squared becomes 4k to the power 2 plus 4k plus 1. And this becomes 2 times something plus 1. And we can see here 2k squared plus 2k is integer 2. It's a linear combination of integers, so it's also integers. And 2 times integer plus 1. So this form is an even number, and plus 1 is also odd number. So this means n to the power of 2 must be odd. So we have proved n is not even, then n squared is not even. So the proof is done. Another fun fact to introduce here, and you are always used in every practice, every problem in future time is here. It's the proud denotion, QED. It's a square, false. It can be empty, it can be full, it can be some line in this way. It means n approved. You already proved it. The fact is proved. And this example is solved. So usually it's right in the right side of the paper, not the left side. I never see some people write it in the left side, but it's always in the right side. To write it means you already proved if n squared is even, then n is even. Okay, and the last example to see from today is called is here. So prove the statement. If x is 10, then 4x minus x squared is not 0. All right, let's see it. This is an example of contradiction strategy. Contradiction. So how to do it is from the previous step we say, so first to set it false, to set it the not form, not something. So this becomes 4x minus x squared equal to 0. We can solve this by our knowledge of a quadratic equation. And what becomes next is here, x equal to 0 and x equal to 4. And what happened? X is not 10. So this condition is contradicted. We say it's contradicted. So x10 is false, which gives like 4x minus x to the power of 2 becomes 0. This is also false, and it's proved again. So I think that's all for today. I want to ask if you have any questions, you can ask here, or you can ask anytime later. Next class, I'll talk about set. Like calculation operation based on set, but maybe not partition. Partition will be in the next lecture. Yeah. So any questions?